All right, well, tell you what, we'll jump right into the lecture for today. If you haven't sent the text, please go ahead and do that. Get that out of the way. So just to kind of recap, in the last class, we introduced to you the fundamental law of electronics called Ohm's law. And Ohm's law says that current is equal to voltage divided by resistance. And this is the standard way of writing Ohm's law, that cause and effect relationship I talked about in the last class. You can see that voltage is the cause of a current, and resistance is opposition to current flow. So you want to make sure that you know and are very familiar with Ohm's law. And as I mentioned in the other class, you should be able to solve for any variable. So I is V on R, V is I times R, and R is V over I. So we talked about that in the last class. We also talked about the relationships between variables, the way you would write those relationships mathematically and what they mean. So one way to write a relationship between I and V would be to use this sign here. This is the sign of proportionality. And if I have two quantities in the numerator, since I is in the numerator and V is in the numerator, we say that current is, and you say this sign means directly proportional to V. Current is directly proportional to V, which means that whatever I do to V, I is going to follow. If I make V bigger, current's going to go up. If I make voltage smaller, current's going to go down. The current's going to follow the voltage. You want to make sure you understand what I mean when I say directly proportional to. The other way of writing this, if I compare I and R, we say that I is directly proportional to 1 over R, or I can say that I is inversely proportional to R. And that means that whatever R does, current will do the opposite. So if I increase the resistance, I expect the current to go down. If I decrease the resistance, I expect the current to go up. Whatever I do the resistance, the current will do the opposite. So we talked about that in the last class. And then we introduced this concept of power. So I gave you a definition for power. As a matter of fact, I gave you two definitions for power. We said that power is a rate of doing something, and the rate means that there's a t in the denominator of the equation. It's a time rate. Power is a rate of doing work, or power is a rate of converting energy from one form to another. And we talked about the fact that power as units of joules per second, it's going to be either work per unit time, or it's going to be energy converted per unit time. But either way, work or energy measured in joules, and time is always in seconds. So watt, so the power has the units of joules per second. We define a joule per second to be 1 watt. We use a capital W for that unit. And then we introduced Watt's law because we said, well, you know, it'd be nice if we can figure out how to calculate power without using these equations that involve T, time and energy and joules and all of that. Well, it turned out that if you take the product of voltage and current, I proved to you in the last class that the units are actually joules per second. So I introduced Watt's law, which says P equals V times I. So if I know the voltage, I know the current, I can get the power in watts. And then we use this, Watt's law, and we did some substitutions with Ohm's law, and we were able to get different forms or different ways of writing Watt's law, which turned out to be pretty convenient. And so what we ended up with for Watt's law, I can write P as V times I. I can write P is I squared times R. Or I can write P equals V squared over R. And so these two laws, Ohm's law, Watt's law, these are the basic tools that we'll use to solve circuits in this class. And I think I mentioned in the other class that this is pretty much it. I mean, we have these 6 formulas, and then we have 2 more laws we talk about, and that's all the pretty much all the equations we'll use to solve any problem this semester. And we did some practice problems with Ohm's law, first few problems on the handout, and then after that I think we ran out of time. So I want to pick up where we left off, which would be problem number 4 on the handout. So if you have your topic sheet, take out your handout, take out your topic sheet, and on the bottom of the topic sheet, you will see problems. I think we already did problems number 1, 2, and 3, and we want to start up today with problem number 4. Now, in the last class, I mentioned to you that you want to use those symbols. You have symbols for voltage, symbol for current, symbol for resistance. You want to use those symbols to draw pictures to help you solve the problem. Now, for the next 3 problems, the 1, 4, 5, and 6, I don't really care if you draw a picture or not, but just kind of in general, try to draw pictures to solve problems. So I'm going to share my document with you just in case you don't have yours printed out, but you do want to have pen, pencil, paper, calculator, all of that so you can solve the problems. So we're going problem number 4, and I will share my document right now and draw the, well, there's really no picture to draw if you don't want to, but go ahead and do the calculation for number 4. I'll give you about 1 minute to do it, and then we'll look at it together. Problem number 4, you have a clothes dryer. The clothes dryer draws 15 amps of current from a 220 volt line, and when you calculate the power used. So notice I made a list here. I list what I'm given, and I list what I'm looking for, and this list tells me which equation to use. I need an equation for power, P equals. It's got to have a V, and an I, and a P in it. Well, the only one with that would be the first one, P, I, and V. That's going to be my working equation. So when doing the problem for me in class, homework, whatever, always start with the equation and actually write it down. I want to see the equation written down. I want to see a substitution with the equation, and I want to see the final answer. So if you were doing this for credit, you would write the working equation down, which says P equals V times I. And then the next step, I would like to see the actual substitution of the numbers. V is 220. I is 15. You do the math, 220 times 15. I don't know what that is, so you let me know what it is. What is 220 times 15?
3,300.
3,300?
Yes.
My units would be, it's 3,300 joules per second or 3,300 watts. Now, how would you convert that to kilowatts? What would you do?
3.3 kilowatt.
3.3 kilowatts. All you got to do to convert to kilowatts, divide this by 1,000. That moves the decimal place over 3 places, and you get 3.3 kilowatts. So it's important to be able to do that, to convert wattage to kilowatts, and you'll understand why a little bit later. So there's your first problem. Anybody have any questions over problem number 4? Okay, well, let's take a look at problem number 5. Here's the document again. Problem number 5, give you a minute to do it. All right, let's look at the next problem, number 5. You have a 27 ohm resistor, has 20 milliamps of current flowing through it. They want you to calculate the power dissipation. So listed my variables. Resistor is 27, current 20 milliamps, P for power. This just kind of happened by accident. Rest in peace, RIP. But so here's my list. I need an equation with an R, I, and a P in it. Well, that would be this one. So my working equation says that P is I squared times R. P is I squared R. I'm going to substitute for I, substitute for R. Now, in the last class, I mentioned to you that normally when I'm calculating these quantities and I have something in K or M, milli or kilo, I leave the K or I leave the M intact, and then I do the problem. Well, here's an exception to that. Anytime I'm squaring a number or I'm taking the square root of a number, I always write it out as a decimal. I just do that because I don't want to confuse myself. Now, since you're doing this on the calculator, as long as you put it in the right way, you'll get the right answer. But you'll see me, I'll always put this in decimal form when I'm squaring something or taking the square root of something. So I want to write I, which is 20 milliamps. I'm going to write that 20 milliamps as 0.02 amps squared times R, so times 27 ohms. So I need for somebody to tell me what you get. You take 0.02 and you square it. You multiply that number by 27. You get a decimal number 0. What?
0.108.
0.018 watts. So I took this out of milli, rolled it as a decimal, squared it, and did my multiplication. And then at the very end, I'll go ahead and write this in engineering notation and then substitute for the correct metric prefix. So if I move this over, 1, 2, 3, I find out that my answer is 10.8. That would be milliwatts. And I would circle it. Now you can leave it like this. I mean, I don't care, but you got to know how to write it both ways. So, I mean, this is a better way to write it. It's easier to look at, but either way, it's okay with me. So 10.8 milliwatts would be the answer. Okay, well, now we'll do problem number 6. Give you a few minutes to do number 6. I'll share my document with you again, and then we'll take a look at it. All right, take a look at this one. This is problem number 6. A certain device has 10 volts across its terminals and a resistance that measures 20 ohms. They want to know the power dissipation. So I made my list. Got a V, a R, and a P. This points to this equation, VRP. So I'm going to write that down. P V squared over R. Put in my numbers. V is 10 volts. R is 20 ohms. It's going to be 100 over 20. I get 5. This is power, so my units will be watts. How many kilowatts is this? 5 watts is how many kilowatts?
Zero point 0.005 kilowatts.
0.005 kilowatts. Again, just divide that by 1,000, and that converts it from watts to kilowatts. So there are some really basic examples of calculating to get power. Anybody have any questions or comments over DC power?
Would you rather the answer have been in kilowatts than just watts?
For that one, probably watts. You'll find out here in just a second why I want you to be able to convert it to kilowatts. I'll tell you that in a few minutes, but yeah, this one, watts is fine. Anybody else? Questions, comments, concerns?
So and this might be a simpleton question, but is power always going to equal watt?
Yep. Well, no.
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 All right.
Power can, who is that?
Jason or John.
John, you sent me a text, and I'm sorry, I didn't respond to your text the other day. I think you said I forgot what you texted me.
I lost connection at the
Were you
end.
able to work it out or not?
I'm working on it. I'll let you know what I come up with. I'll text it to you.
Okay, all right. Sorry I didn't respond to it. I think I saw that I got in the house last night about 1:30 in the morning, and I was like, man, I'm not texting him at that time.
No, thank you.
Okay, so I got a question for you, for everybody, not just for John, for everybody. Let me write down the terms that we've used so far this semester, make sure we understand what we're dealing with, and then I got a question I want to ask you about these terms. So far, on the quiz or exam, I would expect you to be able to define or describe these terms. You should be able to give me a definition for voltage, current, resistance, energy, and power. So let's just kind of review. If I gave you a quiz right now, I'm not going to give you a quiz right now, but if I did, if I gave you a quiz right now, and I say to you, define the term voltage, what would you say? What is a voltage?
Separation of charge.
A voltage is a separation of charge. Nothing more, nothing less. A voltage is a separation of charge. And just like when you separate masses, you develop a gravitational potential difference. When you separate charges, you have an electrical potential difference, but they give that a special name. They call it voltage. So basically, you're creating potential energy, not gravitational, but electrical, because you want to turn that potential energy into kinetic energy by making something move. Okay, good, perfect. What about current? How would you describe or define current?
Charge in motion.
Current is charge in motion. Current is charge in motion. Well, if I have charge and I want to give it motion, what do I need to do that? How do I take a current and make it move? What do I have to have?
Force.
Yeah, you do. And where does that force come from?
Voltage.
Voltage. Who is that talking now? Who is that?
Trevor.
Okay, Trevor said force. I don't think I mentioned this to you. I'm actually glad he brought it up. Remember when I was talking about voltage and I did this? I said, all right, we're going to create a voltage. Here's electrical potential. Once you separate charge and get that electrical potential, then in the region between the separator, you have a field, not a gravitational field, not a magnetic field. So you got charge, you have an electric field. So you have an electric field. And now when I put a charge in there that's free to move, so this charge is free to move, that charge is going to experience a force, and that force is going to make that charge want to move that way. So I never ever told you what that force was. I just said, hey, it experienced a force. You know, like charges repel, so this is pushing that up. Unlike charges attract, so this is pulling it up. While this is pushing and this is pulling, the thing has to move up, but we never named that force. The actual force that acts on the electrons in the electric field is called this. An electromotive force. Electromotive force. Now the reason I'm bringing that up is, remember when we talked about the symbol to represent voltage? You can use this one. You can use this one. Or you can use that one. Well, I think I mentioned, I'm not sure if I mentioned this to your class or not, but the symbol you put here for this, like you put a V there, capital V for volts, but you can also put an E there. You can put a capital E there. And the reason you can use the E is the E off of this. They call this EMF, and that's the way we abbreviate this, electromotive force. So strictly speaking, a voltage and EMF are two different things. The voltage is the separation of charge, and the EMF is the force on the charge that makes it move. But you can fudge that. A lot of people just call it voltage or EMF, and I'm cool with that. So if you ever wonder, well, how come they got an E next to that voltage source instead of a V? Because you can use a V for volts or E for EMF. It doesn't really matter. Okay? So thank you. I think that was Trevor for pointing that out. I didn't think about that force. All right. Okay. So voltage kind of gives us the force to make the electron move. And once the electrons are moving, we have current. And once something's moving, and the current has kinetic energy, and kinetic energy can do work. It can do the work of lighting up your light bulb, turn your cell phone on, running a motor, whatever you want those electrons to do. If you have the properly designed device or circuit, it'll do it. What about resistance? What's that?
Opposition of current.
Resistance is opposition to current flow. Resistance is opposition to current flow. In the macro world, the big world, when things move, we have friction. Friction is the force that opposes motion. In the electron world, the atomic world, when charges move, you have electrical friction or resistance. Resistance is it's not a force, but it's the opposition to current flow. But the friction analogy is perfect because just like real friction, if you in the wintertime you do this, you create friction because you want to warm your hands up. Right? So just like friction creates heat, resistance acts exactly the same way. And that turns out to be pretty important. Resistance always produces heat. Resistance always produces heat. Now, let me ask, is friction good or bad? Is friction good or bad?
It's both.
It's both. It depends. Give me an example where friction is good. Give me an example.
When you're trying to land a plane,
You said when you're trying to land the plane?
like when the tires are hitting the field.
I'll agree with that. If you're trying to run from a dog, or if you're trying to stop your car, you have these brake pads that squeeze against the, what do you call those, the cylinders? I don't know what you call the things you put the tire on, but frictional forces to stop it, right?
Rotor.
What'd you call them?
Rotor.
The rotor. Yeah, thank you. I think that was, who was that? That was Riley. Yeah, the rotor. Are you a mechanic, Riley?
Yes, I do.
You do?
Yes.
Oh, you shouldn't have told me that. All right, give me an example where friction is bad. Why do you put oil in your car?
To make a pressure.
Yeah, to reduce friction, right?
Yes.
So whether friction is good or bad depends on what you're doing. Resistance is exactly the same way. Sometimes resistance is good, sometimes resistance is bad. When you guys come in on Tuesday, we're going to talk in depth about resistance. And we'll talk about some cases where resistance is good or bad, and when it's good, what we can use resistance for. We'll talk about that on Tuesday. What about energy? What is that?
The ability to do work.
Energy is the ability to do work. And actually, it's kind of complicated, isn't it? Because energy is the ability to do work, but we know under energy, there's really different kinds. There's kinetic energy and potential energy. And then related to that is work. And what happens is we start with a potential, and we can make that potential become kinetic, or the kinetic become potential. We can go between one form and the other, but we can't make it disappear. And we can take work and turn that work into potential or kinetic. So there's this play between these joules of work, energy, and so forth. Okay, so we'll go with ability to do work. And then we said power. Well, power is a rate of doing work or rate of converting energy from one form to another.
Oui, bonsoir. Bien? Bien.
He's on the phone.
Dans la classe.
I'm able to do that, guys. I'm able to mute. Once I learned not to mute people, I feel really powerful. All right, now here's the question I want to ask. What do you pay for? When you pay for this stuff. Which one of these, or which 2 or 3 of these? What do you pay for when you pay for something? Are you paying for voltage? Are you paying for current? Are you paying for resistance? Are you paying for energy? Or are you paying for power? What do you pay for?
Energy.
Okay, we got one for energy. Anybody
Power.
else?
Power.
Somebody said we pay for power. Anybody think we pay for voltage? No?
No.
Anybody think we pay for current?
I feel like when you pay for power, you get all of them.
So if you pay power, that means you pay for current use. Voltage and current is in power.
Okay. So that's kind of the same. Somebody said we feel like we kind of pay for all of them. So, well, let me ask you this: who do you pay? Who do you pay for this stuff? Who collects the money?
Energy company or the power company.
Yeah. Who's our power company?
Duke.
Duke Energy. Now, whatever it is you pay for, how do they know how much of it you used?
So it depends on how many hours you use and which charge or which receptor it has been used. So.
Okay, but I'm asking, how do they measure what you use?
They got
What do they
meter.
use? The meter, right?
Meter.
If you go into your basement, right? I don't know where you are. Don't do it now because you're listening to me. But if you go into your basement or outside, somewhere there's an electric meter. All you gotta do is go outside and follow the power wire from, assuming your power wire is above ground. Some power wires are below ground. But most in this city, because the city's so old, most are above ground. If you go to the telephone pole and follow the 3 power wires over to your house and then down that thick cable that runs down the wall, it goes into wherever it enters the building. On the other side of that, there's a meter. Matter of fact, it looks kind of like this one. This is kind of an old school one, but it looks kind of like this. Now, this is an old-fashioned one, and I had this one on purpose because I kind of like this one, because this one actually has the needles that move around. See these meters? See these needles right here? This, that rotates around. All these rotates around. They all rotate around. And these are actually measuring something. What are they measuring? What's the unit of measure for this meter?
Power.
Kilowatts there.
See that right there? That
Kilowatt
KW, yeah, KWH stands for kilowatt hours.
All right.
So here's what happens. Now, they don't do this anymore because they had their high tech now. But back like when I was a kid, you actually had a person that would come to your house. They went to all the houses in the whole city of Cincinnati, and they were called meter readers. And they would do just that. They would read the meter. For example, they come in let's say, January. They come in January, then they would read the meter. And what I mean by read the meter is they would actually come in and see where the hands on these needles were pointing. They read this digit, this digit, this digit. They read all these digits, and for January they get a value. So they got this number, this number. They got these values for January. Then they come back the next month in February and they read the meter again. So they read it in February and get a number. And then what they can do is they can subtract these two, this number from that number, to tell how much of whatever it is you pay for you use. So down here, when they take the difference, that's how many of these things that you're calling kilowatt hours, that's how many you use. So I guess the answer to the question is, since we know this meter is measuring kilowatt hours, I guess the thing to ask is, what the heck is a kilowatt hour? Well, let me tell you. I'll tell you. The way you get kilowatt hours is this. Kilowatt hours, you take the number of kilowatts and you multiply that by the number of hours. And that will give you the unit on that meter, whatever it is, it will give you that thing that they're calling kilowatt hours. That's how they come up with that. So I guess the question is, if we want to find out what this is, what the heck is this thing? What kind of physical quantity is a kilowatt hour? We got to figure out what happens when we take kilowatts and we multiply by hours. So let me ask you this. What kind of quantity is this? Which of these is that over there? What kind of quantity is it?
Power.
Power. So this is power. We're multiplying it by, what kind of quantity is this?
Time.
Time. So the real question is this. What happens when we take power times time? What kind of thing, physical quantity, do we get? And since we know the definition for power, power is energy per unit time, or power is work per unit time. If we use this one, if I multiply this side by T, I got to multiply this side by T. So we see this product of PT, the T's go away, and I get P times time is equal to energy. So this unit, the kilowatt hour, is really a unit of not power. Some people think it's power because it has the term watt in it. But when you take watts and multiply by, think about it. If we said a watt is a joule per second. If you multiply it by time in seconds, you get joules. So this thing has to be energy and not power. So what that meter is reading in your basement is kilowatt hours of energy. Now, if you go down in the basement, your meter probably looks a little different. That's an old meter. The new ones are the LCD, liquid crystal display, and they're actually able to read your meter by remote. They don't have to come out to your house anymore. They can turn it on, turn it off, and read it by remote. And some of the more advanced ones don't even have an LED or LCD readout. It's just a black box, and they can literally, it's basically a computer. But the one you just saw on your screen, it's an old school one. You can kind of really see how it works. So that's the reason I show that. But what you want to remember is you do not pay for voltage. You do not pay for current. You do not pay for resistance. And even though we call Duke Energy the power company, you're not paying for power, you're paying for energy. Now, just like when you buy gas, they sell gas by the gallon. And so you go to the gas station, look up at the sign, and you see the cost per gallon. And you can buy gas. Hey, I don't want to go over there. They're charging $2.11 a gallon. UDF has it for $1.99 a gallon. So if you know the cost per gallon, and you know the size of your fuel tank, you can figure out how much it's going to cost you to fill your car up. If I know the size of my fuel tank, how many gallons I have, and I know how much the gas costs per gallon, if I multiply the number of gallons of my fuel tank by the cost per gallon of gas, then I get how much it's going to cost me to fill my car up. Well, you can do exactly the same thing with energy. But instead of dollars per gallon, it's going to be dollars per kilowatt hour. They charge you by kilowatt hours. They charge you so many dollars per kilowatt hour. So just like if you know how much the gas is costing you per gallon, if you know how many kilowatts, if you know how many dollars per kilowatt hour they're charging you, then you can figure out your electric bill over a certain amount of time. So the question is, how could you find that out? Well, there's a couple places. One is if you get an electric bill. Now, I know probably 2/3 of you never pay an electric bill in your life because you probably stay at home with mom or dad or whatever, but don't worry about it. Trust me, keep living and you'll get a chance to pay one. But for those of us who have to pay our own bills, you know that when you get your electric bill, there's a place for electricity, there's a place for gas. If you look at the electrical utility, if you search on there, you will see a place where they tell you how much they're charging per kilowatt hour. Just like you can look at the sign and see how much you're paying per gallon for gas, you can look at that electric bill and figure out or see how much they charge you per kilowatt hour. And if you know how much they charge you per kilowatt hour, you know how long you're going to use the electricity, you can figure out how much it's going to cost you for electricity. That kind of calculation is called a cost of energy calculation. And that's kind of what I want to do next. So I want you to think about something. Think about, well, let's make an assumption. Now what I'm going to say is true only for this class. We're going to assume, for purposes of this class, the cost of energy is 10 cents per kilowatt hour. So if on a quiz or exam or whatever, if I give you a problem and it's one of these cost of energy problems, but I forget to tell you how much energy costs, just assume it's 10 cents per hour. It's not really 10 cents per hour. It depends on where you live. You might pay one thing in Cincinnati, go across the river in Kentucky, they'll pay something else. Just like gas. Depends on where you live, depends on who your utility company is. But for purposes of this class, we're going to assume cost of energy to be 10 cents per kilowatt hour. Now, having said that, I want you to think about something. Look at this next problem on the handout and see if you can calculate the cost of energy for problem number 7. Look at problem number 7. read it and see if you can figure it out based on what we just talked about. All right, we're running short on time, so I'm gonna give you about one more minute, and I want to talk about this problem so we don't go over. All right, so it says we have a, how much will it cost a 5-watt clock if you use it for 30 days? Now remember, the cost of energy is going to be 10 cents per kilowatt hour. Does anybody have a number for me?
36 cents.
36 cents, somebody said, all right? Anybody have something different?
Well, what was the question, please?
How much is it going to cost to use the clock, 5-watt clock for 30 days? How much will it cost? Number 7. Well, somebody said 36 cents, so let's examine that answer. So the steps would be what? Well, given power, you got to convert power to kilowatts and time to hours.
Mhm.
So here, how many kilowatts is that?
5. 0.005.
We got that by dividing that by 1,000. Now you got to take 30 days and convert it to hours. How many hours is that?
720.
Now, remember what I said about cost of energy? We're going to assume the cost of energy in this class, we're going to assume it's 10 cents per kilowatt hour. The other assumption we're going to make is 1 month will always equal 30 days. So I don't care if the actual month has 30 days in it, 31, 29, 28. Every month of the year for us is going to have 30 days. So if I say in the problem 1 month, I mean 30 days. So you might as well just remember 720 hours because you'll use it. So we got 0.005 kilowatts. We're going to use that power for 720 hours. So how many kilowatt hours is that?
3.6.
3.6. And I always say 3.6 what? 3.6 kilowatt hours of energy, because people tend to think a kilowatt hour is a unit of power. It is not. A kilowatt hour is a unit of energy. Well, you might be thinking, hold on a second, Singleton. Last week you told us that energy was measured in joules. It is measured in joules. But a kilowatt hour is just a big chunk of joules. A kilowatt hour is just a big chunk of joules. It would be like going to the gas station, getting gas, and you want your gas in teaspoons. You drive up to the pump, and let me get 10,000 teaspoons of gas. That would be selling. So what they do, instead of selling you gas in teaspoons, they sell you gas in the bigger chunk. They sell you gas in gallons. If your electric bill was in joules, it'll be as long as this table. So you don't want it in joules. You want a big chunk of joules. A big chunk of joules they call kilowatt hour. So kilowatt hours of energy. So now we know we have 3.6 what? 3.6 kilowatt hours of energy. So if I take the cost, I mean the cost is going to be the number of kilowatt hours times the amount per kilowatt hour. Well, kilowatt hours, we got 3.6. And we wanted it, we don't want it in cents, even though the kilowatt hour is 10 cents per kilowatt hour, we want that in US dollars. So 10 cents is $0.1. So let me write this a little better. I got 3.6 kilowatt hours of energy times $0.1 per kilowatt hour. And now you see why we did 10 cents. That 0.1 is kind of nice to multiply by. Because all you got to do to convert kilowatt hours to dollars is move the decimal place over one place. That's what happens when you multiply by 0.1. So what I get here for cost is $0.36. I convert that back to cents and I get 36 cents. So whoever said this, you're right. You got it. All right, guys, unfortunately, I went over by 4 minutes. Take it out of my paycheck. I mean, what the heck. Anybody have any comments or questions for me before we sign off? Okay, well, a couple things I want to mention. On Tuesday, we're going to have our first face-to-face lab. Please bring a mask with you. Bring a mask. I'll send you the information. I'll tell you what room to come to. You want to bring a mask. You want to bring your meter, your digital multimeter. You do not need to bring your trainer for the lab tomorrow. You do want to have something to write with, all the normal stuff, but you don't need to bring the trainer. And also, I'll put up on Blackboard the documents you should bring in. I think there was a couple things you submitted through Blackboard, like the universal assignment or whatever. But there's a lot of stuff I told you to just hold on to until we meet face to face. Well, I'll put a list up of what you're going to bring with you. And then the last thing is, I think you only had like one quiz, so expect a quiz when you come in first thing on Tuesday. And I'll put some study points up for the quiz to tell you what to look at, because I know we went over a lot of stuff since day one. So, I mean, what do you look at? How you study for the quiz? I'll put some points up for you to focus on and review. Questions or comments before we sign off?
No, I'm all good.
All right, guys. I will see you later. Stay safe. Have a happy
See you.
weekend.
Have a good weekend, all of you, man.
What'd you say, Riley? Okay, guys.
Have a good weekend.
Bye-bye.